Professor Betts asked me to talk, I was ready to look at other people that were likely to give presentations. I thought, you know, what I'm doing is not really computer science. It's really computer engineering. But you obviously have to have the computer science background, which I got here. I'm going to mention areas of innovation that I have been involved with. And of course, this has been a kind of a rough several weeks, having Steve die. I knew Steve, I did things with Steve, and having been at Apple for 31 years, it kind of is part of me. And you know, Steve was Apple, so I went through some issues with dealing with grief and all that stuff, and we had a big celebration last week, which I guess we now posted on the website, which was pretty interesting. The thing that got to me and most people was that we had a commercial right after Steve came back called The Crazy Ones that was narrated by Richard Dreyfuss on the version that people saw. It turns out that Steve actually wrote all of the words for that, and he recorded a version of it that could have been used for the actual commercial, but decided not to use it because he wanted it to be more about Apple and not about him. And so they had the recording there and they played that. And hearing those words in his voice was just, I mean, stunning. Anyway, I started here as a physics major in '61. And my first computer class was, I believe, in '62. It was an introductory programming class in Fortran taught by Howard Schmeising, who was a chemist by trade, as is Professor Lykos. And in those days, the chemists did a lot of computation. That was the time that X-ray crystallography was a big deal, and so the analysis of the crystallography data took a lot of computing power. So they kind of naturally kind of folded over to that area. And this was, on the movie that they were playing at lunch, Ed Reingold talked about the 1620. He and I worked together on a project on the 1620. This is what the system looked like. The 1620 itself is on the upper left, which included the card reader punch and then the actual CPU. And then the thing on the right is a 407, which is an old tabulating machine that was strictly used as a printer. And of course, the printing had to come from punch cards. Everything went to punch cards. So it was kind of cool to have that card as a memorial. Because, you know, I naturally wanted to put it in my pocket like I always carried them. I always had the cards in my pocket because they made great note cards. But anyway, I did this slide very early, and so I didn't do little fancy builds and stuff like I started to. The top shows the way that we typically would run Fortran the hard way, which was a full compiler that would take your card input, produce an intermediate form by punch card output, and then you had to load that into the card reader again with a library for all the subroutines and things that was in a deck of cards also. And then the output went to some more cards, and then you took the cards over to the 407 to get them printed. And I hope that we were recycling, but I'm not sure. I mean, talk about the forests that were denuded just to do an intermediate punch. What Ed and I worked on was there was a system called Forgo that we modified a little bit to work a little bit better for IIT. And that went through just one set of card punch just to get the output, which was a lot faster. Plus, it allowed us to do batching, so we could take a whole bunch of programs back to back and run them through the Forgo processor, which we couldn't with the original Fortran. So the time it took to run a bunch of programs was far less. And that was, you know, as we had more and more students taking the classes and learning how to program, it was kind of important that we were able to get the stuff through as fast as possible. And then we moved to the 7040 and the 1401. And I could probably draw a layout of that machine room right now that would be pretty accurate. It was in the basement of the Commons. It was where a bowling alley had been. And it consisted of the main processor was the 7040 on the right with the little blinking lights and the switches. We were talking about at lunch about how, you know, we kind of missed the old days when they had the real blinking lights and the switches. And you could actually, because of the layout of the lights, which displayed the contents of the registers, you could spell words and send a message across, which of course was great fun in those days. The other thing that was fun was that the 1401 printer was a chain printer, and you could play music. You could play a tune with the right sequence of printing, which was absolutely totally useless except for wasting paper. But of course it was great fun. And I'm a hacker, or a computer bum, and always have been. It's been very fortunate that I found myself landing in positions where that skill turned out to be useful to somebody, and I was still having fun doing it. And certainly that's been my history at Apple. Steve in his commencement speech talked about, you know, finding a place that you love and then do that. And I found it, you know, that was where it was at. We had a big drum, mass storage device, mass storage. What was massive about it was the storage device itself. It had a compressor that had to be approved by the city because of the pressure that the thing ran at to drive the heads through the disk. And the disks were about this big around. And you had to have it positioned and locked so it wouldn't walk. That was another fun thing you would do in the old days, is to try and walk your disk across the room, because from the head motion of the thing, right? And it had a massive 25 megabytes of storage. The 7040 had 36-bit words, which God intended, 32K. The 1401 was strictly used as a way of getting data across between the machines. Now, it was via mag tape, so there were also some magnetic tapes associated with it. And the flow originally would be, you go from card reader to 1401 to a tape, and you physically take that tape and you go over to the tape of the 7040. You would run that through, which would generate your output tape, and you would take that tape off and you would move it over to the 1401, and then that would go to the printer. Well, we kind of looked at that, and this is where, you know, one of the innovations was something called spooling. And with spooling, what you did was, there's enough, you could make it interrupt driven. I mean, you gotta realize that 32K words is not a lot of storage. I mean, for a program. There was enough room for a small interrupt-driven program to be able to take data from the card reader and go to the printer while you were running stuff in the background, regular user programs in the background. So I put together this little spooling system, and we would go from the card reader to a tape, and then that tape would be switched over to the 7040. Now, you wouldn't physically move the tape, you would just physically do the interconnect. Not physically, it would be done automatically, electronically. And that would produce an output tape. And then the output tape would be switched again and read as an input by the 7040, which would then connect and go to the printer. So this saved us physically having to take the tape back and forth. And again, the whole idea was we had all these students running, and not only students, we had a lot of people that were running, you know, their normal physics simulations or chemistry simulations, whatever. And the whole game was to try and get stuff through the system as fast as possible. And then we got to the big time. We got a 360 Model 40, and that's the nice panel with all the nice blinking lights and things over there. We upgraded, the storage was, we had 4 2311s with little disk drives. They were made to be removable disk drives, but we never removed them, which were only 7.5 megabytes each. There were some tape drives, but we didn't really use them for most normal processing. The disks were sufficient. But we had a 2701. Now, 2701 is basically a UART receiver. And what that allowed us to do was to connect to the outside world modems on teletypes, and there's a couple teletypes up there. And these were out in the high schools in the area so we were supporting, you know, what Charlie Bauer put together, this Computel network, where instead of having kids come down to IIT on Saturdays to run programs, they would put the programs out on paper tape. Someone would batch those in, call up our machine, batch those in, we would suck them in, and again, this could all be done while we were running other stuff in the background. And then at some point, we'd process all of the data, and this, of course, was written in ITRAN. And ITRAN wasn't really based on Fortran. It was a easier to use, cleaned up version of PL1. It was more like PL1 than anything else. And that was Bill Worley from the University of Chicago who did that. He and I kind of invented the language, and then when Dewar came over, we ported it over to the 1108 and kept it going. So I actually have a paper in this CACM in 1968 that's on ITRAN. It was actually a quite advanced language, and it was a very nice block structured language. Easy for people to learn. It didn't have, you know, the fixed formatting of Fortran and all that garbage. But that's what we ran for the high school. So they would learn ITRAN programming, paper tape in, then they dial up later and get all their output, you know, and which the school students would then pull off. So it was, we were one of the few places, I think, in the country that were doing anything like this. And the cool thing is that shortly after I got to Apple, I found out that one of the guys who was in the Mac OS group, the original Mac OS group, had gone through that class. And that's how he had learned computer programming. So that was kind of cool. The other thing was, a couple of weeks ago, I was listening to an interview of Ward Cunningham, who is the inventor of the wikis. He learned the programming through IIT. And I had never known that before, but he mentioned it. I said, oh, wow, that's cool. So, you know, in some way, we touched the lives of people and kind of got some more programmers in the world. Then we went to the heavy metal, the big stuff. We went to an 1108, which was a much bigger, faster processor. Again, 36-bit words, but this time it was 128 kilowords. Fast ran, so we had a much bigger storage device. It was huge. It was a dual drum, drums this big. The maintenance manual said that if you spun down the drive and it took less than 20 minutes to stop, you had to replace the bearings because it meant that the bearings were going. Stored 132 megabytes, which was pretty good size in those days. And then we still had this card reader punch. The 1004 was a card reader punch that connected into the system. By this time, we were doing spooling of it. And then we had an FCC 4700, which was a little mini computer in those days. And it had two big things going for it, which is why we chose it. One is it had an incredibly cheap UART interface, again, asynchronous interface for connecting into the teletypes. by using very simple hardware and then a magic microcode instruction that would cycle through the data that you would acquire and build up the characters for you in memory. I'm not used to this. So it was a very good way of expanding the number of lines that we could handle. And it had a direct high-speed channel interconnect to the 1108. That was the key. That meant that we could really move data back and forth very cheaply and very quickly. So I wrote the ITROS operating system, which stood for either IIT Remote Operating System or IIT Ron's operating system, depending upon who you were. And that was the machine that was there at the time that I went off to Fermilab. And Fermilab was a fun place to be back in those days. I was working on the target experimental sites, not the big ring control system, which was impressive in its own right. And those were really fun days to be there because the ring was just coming up. I mean, the place was still under construction. We were in a portable building that was more like a meat locker. The outhouse was outside. There was no running water. And so it was an exciting place to be. Just for, you know, you felt like you were on the prairie, especially when you go by the bison every day. It had a storage display, which was a very interesting device. It was basically an oscilloscope that had a long persistence phosphor. And so if you wrote it, it would stay there for a long time. And so we used that as our graphics display. And I wrote the library routines and stuff to put up the, you know, to draw graphs and characters and all kinds of funny graphics and things. The other thing it had was something called KMAC, which stood for Computer Automated Measurement and Control, which was a standardized way of connecting your physics apparatus and get it into the system for processing. And the KMAC box that we chose was built by EEG in Oak Ridge, and they were just debugging it. And so it was a perfect place for me to be at the time, because I got to test and develop the hardware at the same time that they were bringing it up. And originally they would fly an engineer out to go over and work with us, and then eventually they just got to the point where they give me a call and I take out the wire wrap and we make the changes and stuff. And it was a great place for me to hone up on my hardware skills. As Dr. Bitts said, the way I describe myself is I'm a software guy who knows more hardware. I'm a software guy who knows more hardware than most software guys. And I'm a hardware guy that knows more about software than most hardware guys. So I'm kind of a system integrationist. I've done hardware, I've done chip design, I've done boards. I've done programming languages. I mean, whatever it takes. Most of what I've done is innovate. You're faced with a problem, and you don't even have a set of specs because you don't know what the thing's what you really wanted to do, and so you have to start playing until you finally get to a point when you have something that seems to be working. After a couple years at Fermilab, I decided I'd like to go into teaching because I love to explain things to people, and I'm reasonably good at it, so I've been told. So I decided I would go back to school and get a master's. I didn't graduate with a master's from IIT. I graduated with a bachelor's of science in liberal arts with a computer science major because we really didn't have a computer science department quite yet. And so I went to Purdue for a year, and yeah, that's my big thing. I got an A+ in the course from Peter Denning, which back in those days, you know, if you know operating systems, that was fun. And I taught introductory programming, you know, as a teacher's assistant kind of a thingy. And I really liked it. But then I have a little bit of ADD. And there was this bright, shiny thing that someone dangled in front of me. And they said, how'd you like to work on a summer project to do some programming for this doctorate at Northwestern University that was doing an NIH grant, and they needed some kind of support for a little database system, a little data capture system. And so I said, okay, I can start playing with that. And so I started doing that, and that turned into a couple-year commitment to actually get the whole thing up and running. And I did implement a database. I gave a talk at a DECAS conference once about that. This was in the days when people were writing their own programming languages, so I wrote my own programming language called NewLang, which was written in a meta-lang programming language called NewMeta. That was, it was interesting. I'm not sure it was worthwhile, but this is, remember, this is before C. This is before a lot of the programming languages that people have around today.
I was at that.
Ah! And it was using threaded code, which is kind of what the DEC Fortran compiler used. And I think Robert Dewar wrote an article on various, yes, the very article about various ways of doing threaded coding. And then IIT.2. What happened was I was working on this, so this research project was winding down, and I guess it was Toby, who, I found out about that they were teaching evening courses, and they wanted some instructors for some like operating systems. And I know a little bit about operating systems, and so I became a teacher in the evening division, which was very fun because you got a lot of outside people coming in to learn about computer science and operating systems in particular from the outside world. So it actually turned out to be a very fun thing to do. And eventually I became a full-time instructor in the department. Operating system courses, assembly language, database course. I did some programming languages too. But the fun part was a microprocessor programming class with Mark. Where are you, Mark? Mark Kondik. And it involved a 8008 hand-built board so that you got a kit when you took the course, and you had to assemble the kit and then, start programming it. And 8008 was not exactly a modern microprocessor, but it was a, It was then, yes, that's true. And this actually turned out to be very useful in stuff that I did later. Then I decided that, for a variety of reasons, which are an interesting backstory in its own, but I decided I wanted to move out to Silicon Valley. And I picked up saw an ad in the paper about National looking for people to work on an IBM clone. The chip makers a long time ago decided that they don't make a lot of money on chips, especially the small chips they had back then. Instead, if they put them together and sold them in a box, they could charge a lot more money. And so what various people were doing is to try and build these 370 clones, which the Justice Department said they had to be able to do finally, when IBM suit and all that. So that's what the project was involved. It was I wish I had some pictures of it. I saw some pictures on the web, but they didn't exactly hit me. It was a big box with big boards, all hand-wired, using 8-bit, or actually, yeah, 8-bit slices, bit slices for doing the arithmetic with programming logic that was really bleeding edge at the time, but not really that super great. So as in a couple of things that I've done, I was hired to implement the microcode assembler, and what I usually end up doing is not doing what they hired me for. So instead I started working a lot on debugging the actual CPU microcode, which was a lot of fun. And then the channel microcode, the guy who did it was just totally bonkers, and so I rewrote all of that. And then I ended up as a consultant to the engineering VP, technical, like CTO of the little group that we were in. Then something happened that was not unusual back in those days. A whole group of us went over to Apple en masse, like 8 of us. And I honestly did not know anything about Apple when I did it. We were working on Lisa. Now actually this is what the products were that I've had involvement with. and I'll describe those. So Lisa was originally conceived to be a character-oriented business kind of a system. And it had a 5 megahertz 68K, which was kind of state of the art back then, a whole megabyte of RAM. So I was hired to work on LisaCalc. The Lisa had an open hardware system, so there were expansion slots that you could build cards for, but it had a closed programming system. We wrote the programs, and you better like them, or that's it. We didn't allow third parties to write programs for them, which was a huge mistake. But then I wandered over to the hardware lab and never wandered back. So I've been more or less in the hardware group ever since. And then came this visit to Xerox PARC. So we were this character-oriented kind of blasé thing. And I was one of the people that went up with Steve to visit Xerox PARC when we saw the Star, the Alto, and then the Star system, which was all GUI. You know, it had these little icons, it had a little mouse that would move things around. And we became so enamored of it that we decided to just scratch what we were doing and change everything to go over to this graphical user interface. And one thing we did was we then had an offsite of all the people that were working on the project at Pajaro Dunes, which is a little place on the seaside near us. And Steve led the meeting, and we had this little football, and if you wanted to talk, you had to throw it to somebody. It was a token. It was the speaking token. And so that's how we managed the meeting, because everyone had all these wild ideas. And a guy named Bill Atkinson had put together a little demo of something that would be the graphical user interface. He's the one who wrote QuickDraw in the early Mac days, and was really the major influence on a lot of the graphics part of the user interface. And then the rest is history, because that's, you know, when we came out with the Mac, with the GUI and stuff, it just kind of like blew everyone away. During that time with Lisa, we decided that one of the things you needed to be able to do in a business environment was to connect these things, network the devices. And Ethernet was just starting to be used widely. And of course, that was a 10 megabit system. It had these big cables. We decided we would do something a little bit different, similar, but it was a slower network, but it was easier to cable, easier to work, and you know, we really integrated it into the system. The one cute thing about this, it was very technically innovative in the sense that the guy who designed the interface made it was a toroidal coil that was used to inject our own signal and receive someone else's signal. And with our system, we could transmit data and not see our own data on the input side because of the way that these magic cords were wound, which was a lot easier to do and cheaper than what Ethernet was doing, which was actually doing energy measurements and stuff of what was on the wire. What enabled to do this was that at least it did have an expansion slot. It was open hardware. And then I decided, since it was hard to get the software guys really enthused about this, I implemented a block server. So it wasn't a file server, but it was a block server. It's basically providing virtual drives to all the Lisas that were connected to it. You each had your own little virtual disk, including a print server. And these were diskless Lisas. So we actually, in the factory, had this like 6-tier high by maybe 50 wide for burn-in, have all these Lisas sitting there with no disks, connected over AppleNet, and then one little Lisa that had a little display showing which machines were alive and which were dead. We could boot the system. We could load all the programs and things from over AppleNet. It was really amazing, and it took us a while to get to that point in the Mac. The laser writer, someone here from Adobe, the laser writer came along next. That was in '85, so we introduced the Mac in '84. In '85, we introduced the laser writer, and I had a lot of fun talking with Chuck Geschke and John Warnock about PostScript. It has to come out now. I am a fourth programmer. Now, right, a lot of people go, ooh. You know, some people don't consider fourth a language, but it's great for what we were doing. And it turns out that PostScript is very much like fourth. And I had arguments about how much alike it was. The point about it, however, was that it really required a network. And this was meant to be used with a Mac. And the Mac didn't have an expansion slot. So we were faced with a conundrum. This is where a little bit of innovation helped out. We had a group that was doing a high-level protocol that was, you know, it was on the level of TCP/IP, except it was our own, because we had a tendency to do that back then. But local talk was the physical link layer, and that's what I worked on. And it leveraged the fact that we had a built-in UART, a built-in SCC, which has some pretty cool capabilities for doing high-speed synchronous transmission. And what I did was we implemented it was a 200 kilobit per second CSMA, sort of. The trick was that you couldn't really detect if someone else was on the wire. You had to do a funny little protocol to try and tell if someone was on the wire. And it was a little bit hokey, but it did work, and that was my first patent. The Mac 2 was our next box. The Mac 2, I was the systems architect for. It was a Mac with slots. Then we were faced with this problem, what slot do you use? And of course, ISA was there, and there was microchannel. And we decided to go with NuBus. So I spent several months working on the IEEE 1196 committee to standardize NuBus, and then did the initial implementation of the NuBus interface. So 32-bit wide, 10 megahertz bus. It was very easy to interface to, geographically addressed, and self-identifying cards. And this was unique in that time period. This meant that the software could tell what card was plugged into what slot, and even include a driver on it. And this was still in the days when BIOS was playing with ISA things and flipping switches and configuring your drivers and all that garbage, and this kind of automated the whole process. And along the way, unfortunately, then I became Mr. NuBus because I was on the committee. We had several IEEE extravaganzas that I went to and gave lectures on NuBus and talked about it and stuff because it was to our advantage to get more people knowing about it so they could build cards for us. And then there's PowerPC. PowerPC came about because we decided at the time that the 68K was not going to, that CISC architecture was not going to be the future. And so we had a group that I was a member of that were looking at various RISC architectures. And we were looked at MIPS, and of course another thing to consider is that we had Patterson at Berkeley and we had Hennessy and Stanford both doing RISC stuff. So we kind of had to do RISC. And we were looking at a couple other choices to pick. We looked at Spark, SunSpark, and hello? Seems did this go dead? Anyway, when we got a call from IBM, we had the president of IBM called John Scully, who was our president at the time, and said, why don't you guys look at us? Because we have a RISC chip. And at the time, their RISC implementation consisted of 7 chips on this big board, and we didn't think there was any chance we could possibly use it. We hadn't even looked at it. So we decided to go back down to Austin and investigate. And there's this classic story where we were going to be talking to IBM, and we didn't want to appear like the country bumpkins we were. So we were dressed in suits. IBM Austin is a little relaxed anyway, but this was Friday, and Friday was a dress-down day. And so the IBM guys were in jeans and shirts, and we were in the suits. That never happened again. And what happened about that is we formed the PowerPC Architecture Committee. We made a joint venture between IBM, Motorola, and Apple. We worked on the architecture and defined it. The summer of '90, we spent flying to Austin on a Monday morning, spending all week in Austin, flying back on a Friday, and then doing the same thing the next week to develop the architecture to something that we thought we could live with in terms of simplicity, what we thought could be scalable to the future, the AIM Alliance. And we eventually did it, and my signature is on the official Apple representative of the architecture, for what it's worth. It was a fun time to be involved, and it was a great, great social experience, watching all these engineers arguing about the subtleties of some instruction. The Smurf card, one of the things that I did was to allow our programmers to have early access to being able to write PowerPC code. IBM had been working on a chip called the RSC, the RISC single chip. It was a weird chip, it had a weird interface, but we decided to build a card that could plug into a Mac too. So I built a new bus card that had the RSC chip on it that could take over all of the hardware on the motherboard and drive all of the I/O. So we could really run a full operating system by running it off of this chip. And so I built this little card, and we had to come up with fun names. And so I called it Smurf card because it was a little blue thing, right? IBM, little blue. When we terminated the program, or later on, they gave me this little Smurf doll with a checked flannel shirt with a pencil, with a pocket protector in it, because that's how I dress. I have a picture somewhere of Truth in Advertising. This is not what I wear every day. Altivac was something that was a fun project to work on, and one of the things that I've done, which enables me to kind of keep up with what's going on, is I've been a member of IEEE and of the ACM ever since I graduated. And I had just read an article that Berkeley had done on this SIMD chip, single instruction, multiple data. And we were looking for some way to compete with SSE, which Intel had been doing, of course, Intel being the bad guys. And so we decided to go with this Altivac. So we formed a committee, again, in the PowerPC architecture group. We defined the Altivac architecture, and we built it. And it still is a very interesting architecture for doing a lot of vector operations. Intel has since gone to SE2, 3, 4, 4.1, and then they have AVX, and then of course it became Mr. PowerPC, because then I gave classes on PowerPC to all the programmers at Apple. I gave a big presentation to our Macintosh developer group on PowerPC. So in a sense, I've had the ability to teach, even though I wasn't, teaching at a school. The PowerMacs that we started building, we decided to go with PCI expansion slots. Then we decided that we needed a new BIOS. And of course, BIOS was what Intel was using on their boxes, or Microsoft actually. And so we decided to go with, I decided to go with open firmware, which again, formed an IEEE committee to define it. It's forth-based. It is, the code is stored in an F code, which is strictly a real simple transliteration of the source. It's strictly a tokenized version of the source. And that F code could then go in expansion ROM. So we were able to build cards that carried the driver with the card, which really helps when you're trying to build easy to use systems for users. And Apple, that's one thing that Apple has always been about. Make it just work. Don't require the user to read the manual, flip the switches, configure the BIOS and all that. Just plug it in and it works. And this is one of the things that allowed us to do that. I did the initial implementation on that and then guided the guys who were doing the rest of it. One thing that I'm very proud of, even though it never really turned out to be that useful, was PowerPC had the capability of running in big endian or little endian mode. Okay, and so I wrote open firmware, and it turned out not to be that hard to do, so that you could just set a configuration switch in NB RAM, reboot, and it would reboot in Little Endian or in Big Endian from the same source base, from the same F-code image. It was pretty cool. Even the IBM guy didn't believe me when I told him until I showed him, and then he looked at it and he said, oh yeah, that is Little Endian. Because we actually were able to boot NT, because Microsoft was claiming that NT was not just for x86, but you could run a PowerPC, and we did actually boot NT. Then of course it became Mr. Open Firmware, because I had to teach classes on how to write F-code, and other people in the company of how to support the F-code. Then my other piece, the resistance, is the Power Mac G5. This was another issue where IBM called us and said, we have this superscalar big machine that we would like to be able to put into a single chip, and we think you guys could use it. And so we went down, and two of us went down, had a meeting with them, and it looked interesting. So that was called the 970. It was the first 64-bit, well, it was the first commodity 64-bit version of PowerPC. It was massively multi-issue. It had 8 execution pipes. It could do 8 fetches of 8 instructions at once, could decode and dispatch 4 at a time. Dual floating point units. It had could handle 200 instructions in flight. It was totally, massively out of order execution, which was, I mean, it's really cool. But it had a funny thing about it. Most microprocessors have a reset pin. And normally what happens is when you turn the machine on, the reset gets hit, and then the chip comes up and starts executing the way it's supposed to. Well, from the days of their being built for workstations, IBM didn't think they needed to do that. So you required a little support processor to jam enough state into the chip before you released it so it could start executing. I got very involved in JTAG. JTAG's this magic interface that lets you talk to the chips at a very low level. And we would send in these scan chains, and I think it was on the order of 22,000 bits that had to be stuffed into the thing before it could start executing. So we implemented something using a little MSP 430. And this is one of those things where I was starting to play with the micros myself, and it turned out that that was exactly what we needed for this case, and so I had it out of my back pocket when we started thinking about this thing. And of course, it's coded in forth. The one thing about that was cool about that was that we could walk up to a machine. Now, they had built a whole bunch of debugging hardware into their chip and our chip, and we could take a machine that had locked up, that had frozen, and connect into a serial port into the SPU, and then scan out the contents of the state of the machine and look at all of the registers and look at the state of the cache and look at all the, and it was like magic. We could do hardware debugging on a machine that was totally dead because of the way that they had implemented this little interface, back-end interface. It had a new interconnect, so it had a totally new bus. Buses in those days were designed to be everyone connected to the bus, and someone would drive the bus, and everyone else would listen, and then if someone wanted to respond, they would then, you'd turn the bus around, they would drive the bus, and you had all of these signals going back and forth. You had to have some time delay between that, so you weren't driving at the same time. It was a mess, and so we decided that that wouldn't work for a speed, for the processor speed we were talking about. So it was a short synchronous bus, which means that it had, each chip had an outie and an innie, so it would drive the output side with its own clock, and the clock would be recovered on the other end, and vice versa. And so you never had contention for the bus. The bus was always running, and it all either carry, a lot of times it was carrying idles, but it would also then be instantly ready without having to worry about turnaround time. But we had this problem with, IBM was designing the CPU in Austin in a programming language called VHDL, which I want to just mention, nowadays everything is software. Chips are software. Hardware is software. They write a big Verilog program, basically, which describes the operation of the chip, and then that gets instantiated into silicon. And that is, so it's a programming effort, it's a programming project, design your own processor. But they were designing it in Austin. We, of course, were in Cupertino, and we were doing everything in Verilog. And so now what happens when you want to design a chip that's supposed to be what we call a north bridge? So you have the CPU, in typical diagram, you have CPU here, and then here's the north bridge, and then here's the south bridge. But that's what sort of memory interface and stuff are on the north bridge. How do you check out that you're doing the right thing when you're talking on the bus, when you have a new bus that no one has ever implemented before, and you're not even sure the protocol's right? And so we had many meetings with this. We wanted to do this co-simulation. We wanted to be able to simulate our chip at the same time that their chip was running in a simulated environment. And I was listening in on some phone calls we had with the project leaders at the time. And they were talking about, well, we could translate VHDL into Verilog, and then you guys could run it over there, and but it would take forever. You couldn't do it perfectly. How do you keep up with the latest version? And so I said, what if we just simulated the bus transactions remotely over TCP/IP between the two sites? And they said, huh? And then they said, it'll never work. So I built a little prototype, and we had a group in actually the design center that had some machines there. I talked to one of those guys. He hooked up the machine. I had a machine here, and we simulated doing the bus transactions. And it would take a long time relatively in terms of milliseconds to transport the packets back and forth. But you got to realize these are huge chips. The simulation time between doing a bus cycle is forever. So the fact that it takes a few milliseconds to transport a packet worth of bus data was lost in the noise. It didn't have any effect. So we did remote COSIM. And so it's basically two TCP/IP streams. What made it a little difficult, of course, is that everyone had firewalls, and so you couldn't open up a connection to the other side without going through its firewall, which they didn't want to face their IT people and have to deal with. Let's see what Gus has left. And so what we did was we implemented a rendezvous agent, which for every clock would wait for output from both ends. So first of all, they would rendezvous, and then they would connect. And then the rendezvous agent would take the output data from both sides and then reflect it back to the other side, and do that on a clock-by-clock basis. And that's what it ended up looking like. And that was a huge win because it allowed us to completely automate the whole testing process. We eventually added some facilities so we could start up a job on the other side to run a simulation and automatically logging and all that kind of garbage. And this really saved us a huge amount of time in being able to do the chip. The last thing I want to talk about, although not much, is Thunderbolt. And someone was mentioning about the architecture and using optical interlinks for connection. Originally, Thunderbolt was supposed to be optical. And it is designed to be able to be run optical. But in our implementation, we chose to make it copper because we could leverage the one DisplayPort connector we already had on all of our machines. So we implemented a system that would, it's a packet basically at 256 bytes at a time. It's a very clever technology. We spent, again, a whole summer implementing or arguing the architecture with Intel. So this is basically Intel-Apple joint project. Path routing to get the data between everything. You could have multiple stages of routers in the path, so you can daisy chain boxes together. You can use it as a hub to split out things like you do with USB, but it's running at 10 gigabit. It supports what we call native CIO, which is a way that we transport data. We have a TCP/IP stack running between machines over the 10 gigabit. We do TDM, which is where you can talk to another machine as if it was your local disk. It runs tunnel PCIe, so you can build expansion boxes and put PCIe in cards on one box and just use this to route between them. We have a bunch of people doing RAID devices that way. It also carries tunnel to DP. So we can take DisplayPort output and tunnel it so it gets converted into digital format, digital packet format, sent over and then reconverted back into the DP analog format that the displays would take. And most of our developers are like the RAID boxes. You can plug in a display out the back end. So it ends up being a dual purpose thing. And that's what I've been working on until fairly recently. What I'm doing now is working on simulation of the next generation iPhone processors, which are fun. That's basically all I have. What I would try to do is to show you how, even in an engineering context, there's a lot of innovation that can be had if you just see that there are solutions that can be made that aren't necessarily obvious. And I've had the wonderful opportunity and incredible luck to have found the right place at the right time to be there for it. And I started here at IIT, A computer bum turned useful, maybe.
I omitted to mention that Ron's title at Apple is Distinguished Engineer, and it's very clear why that is so. You weren't responsible for the dreaded Bison box, were you, at Fermilab? No, okay. No, so we got time for a few questions. Federica. Yeah.
To ask you, where do you see the multi-core technology with, they say thousands of multi-cores on a chip. I would go for the near future, hundreds. And with optical interconnect and also optical switching on the fiber. So where do you see these capabilities that will be coming in the near future figuring in the Apple kind of environment?
Well, we definitely have, we have a lot of multi-core processors that we use and build with, and we work with Intel quite closely on the architecture of those systems. Intel kind of loves Apple because we're one of the few companies, I think we're actually the only company, that's able to take the technology and completely implement it from bottom to top, hardware, software, drivers, all that stuff. No one else does that, and it takes them forever to get Microsoft interested in writing a driver for something, and we're like right there before it's out. So they love us because we're a pull for them, for their technology, and that's something that they're very interested in. So and that's the same thing with CPUs. We've been working with multi-core for quite a while. The G5 was a multi-core, and we had a box that had 2 of those, so we had a 4-core PowerPC. My desktop machine is a 12-core, 24-thread, 24 gigabyte RAM, 3 terabyte RAID system. That's my desktop.
Can I ask
No. So we have a lot of interest in multi-core. The big issue for us in multi-core is how to figure out how to use them efficiently, which is the problem.
So my question actually was going beyond the 4 and 8 and 16 cores on it was, the upcoming 100.
Actually, I have a chip that Intel
Where
has a show-off day every couple months, and we went there, and someone handed me, I've got a non-functional, but an 80-core chip on my desk. And they were actually building platforms to give to universities to try and do something with them. The issue with the multi-cores, there's a couple issues. One is, and then we've been having a lot of discussion, do you make all the cores the same, right? That's a huge issue because you could build a system that had a lot of little cores and a couple big cores. And if you could have an OS that understood how to divvy up the work so that they could be useful, you can fit a lot more of those in than you could big cores. The problem with big cores is that they chew up an awful lot of power. So it's very hard to put too many cores on a chip without melting. But there's also the software issue. The issue of how do you partition your applications and how do you transfer the data back and forth, especially if you're in a system like ours, we have, say, multiple chips, multiple sockets. if you're unlucky enough to get your application moved from here to there and your data's still over here, you lose an awful lot of time getting the interconnect. And even optical, I mean, you can make the interconnect as fast as you want, but it's still not going to be as fast as if it was like locally there sharing all the caches that you filled up and have to just go and refill again. One of the things that we have done is we worked to come up with a standard called OpenCL, which is a way of writing programs in a kind of machine agnostic form that can be then JIT, just-in-time compiled to a target like the processor, the GPU, and be able to run programs that way. And then we have, our OS actually has a dispatcher that takes these little blocks of OpenCL code and will then dispatch them, to whatever free CPU is available. And we're trying to go in that direction of writing code in a way that lets us be more agnostic about which particular processor you actually end up running on, because this gives us a lot more flexibility in mixing and matching little cores, big cores, GPUs, all that kind of stuff. So we recognize that that's a problem, and we have tried to solve it from the software side with some of the programming language efforts. But it's a big problem.
Other question? Yeah, Frank.
I was going to get with the connected with the previous comments. When you see the role of GPU computing, and you can see using the further role interface to have external number of crunchy boxes, you can plug use GPUs in the box for having to be
Yeah, I mean, the problem there is, again, how do you get the data back and forth? Because the GPUs are going to require some amount of storage coming from from somewhere, and that's a big problem with GPUs now, is getting the data back and forth between what the main processor wants to do and the other one. As far as GPUs, we're kind of, and I think Intel is assuming that also, is that we're going in the direction that you're going to have a unified instruction set that's going to be flexible enough to match the capabilities of the GPU to some extent, to a large extent, large enough extent that it doesn't pay you to implement a specialized processor. Okay, and I don't know how many are familiar with a thing called Larrabee that Intel was doing. It was a funny instruction set that was designed specifically to be used for graphics type processing. So it was a GPU, but it turns out that you can fold the instruction set into the existing instruction set. And Intel has done this marvelous job of every couple of years adding, implementing a whole new vector unit, which is like twice as big as the previous one, or 4 times as big. So I started with SSE. They're now up to the AVX, which I think is 256, and Larrabee was 512-bit registers with a brand new instruction set. The problem you have with the Intel architecture, of course, is how do you squeeze the opcodes in? It's a CISC architecture fundamentally. Now, actually, it turns out there was this big war a long time ago about whether RISC or CISC was better. It turns out that it doesn't make any difference anymore, because you can throw enough transistors at it so that you can take a CISC outside to what the programmer thinks he's coding in and translate it on the fly into RISC. And so the guts of all of the Intel cores nowadays are RISC inside, but they do a translation from CISC outside to go in. So, and so both won. But it's hard to, so the CISC decoding, Intel is running into a limit that they had a long time ago of the length of the opcode field that couldn't exceed 15 bytes. Now, realize that the shortest instructions can take 1 byte. And so you have these long instructions, especially with 64-bit addressing and 64-bit immediates and stuff, you can start chewing up a lot of bytes in the opcode. That gets very tricky. And of course, you have to be careful about squeezing the bytes in. But I think that they're going, and other people are going in the direction of trying to make the capabilities of the CPU be able to be close enough to what the GPUs have done, so you don't have to have 2 different programming worlds. I mean, that is an issue of, even with OpenCL or something, it's still a mess to be able to try and code in a way that can use both of them efficiently, because you have to go for the least common denominator kind of a thing.
an amazing story.